Hi, I'm Alberto Barbati, and I am going to talk about STD generator. Um, just to know you, how many of you are using C++20? Not many? Okay. How many do you use coroutines? No one. Okay. No, I know that because coroutines. How many of you are using other languages with coroutines? For example, C#. Okay. No, because people who know me knows that I like to talk about something that is going to come, not something that you have it right now. And also, I like coroutines, so I'm going to speak about STD generator. STD generator is, no, sorry, too much. Is a new facility that is coming with C++23 and is based on coroutines. So what best to start to talk about. And we will introduce this little library. We will see a couple of motivation and use cases. We will try to compare generators with the traditional approaches, so which are the pros and cons of this approach. And if you are using C++20, we have a reference implementation, not me. The proposer of the library has provided us with a reference implementation. So if you want, you can use it right now if you are using C++20. Okay, so just another question. Who are using ranges or are familiar with ranges? Not many. Okay. So I prepared a ranges for dummies a slide to get into this. Okay. You all know this. This is easy, you know? This is a for range loop. Okay. So what is range? Is whatever you can put here. Easy. More or less. Okay. Just to give some more details. Let's explode. You know that this syntax here is actually syntactic sugar for something else. And what else? This thing. I hope that you can read it. You just evaluate the expression and assign it to a variable. Then you call begin and end on this variable. I wrote the member begin and end. Actually, you can also, if the compiler doesn't find member begin and end, it will call the free function begin and end. And there's also some special case for arrays, for C-style arrays, but we don't need to go there. And then we start the normal loop with this iterator. You just check if the iterator reaches the end, and then you increment the iterator. Then you dereference the iterator and assign it to whatever you put here and execute the body. So actually, this thing is syntactic sugar for this. However, looking at this code, we see what are the minimal requirements for a range. A range needs to have a begin and end. These two functions need to return something. Actually, it must be an iterator, so it has to have at least the increment and the reference operation, and need not be an iterator. Used to be so in the first C++ version that introduced the for range loop. Actually, and can be a different type from the iterator as long as we have the comparison. And this is interesting because you can have ranges that where the end is a special one, and it's called like a sentinel in the terminology of the standard. And so here we are comparing with the sentinel. The sentinel can be anything as long as you have the comparison operator. Okay, So now that, sorry. Okay, so let's start with motivating examples for the generator. Let's start with something that doesn't have a generation. That doesn't use generator. Fibonacci numbers. It was mentioned in the previous talk because it's easy. It's something that generates number. You all know Fibonacci numbers. There's a sequence of integer that is 1, 1, 2, 3, 5, 8, 11, etc. And this is a little function that generates Fibonacci numbers. You can write it in a lot of ways. I chose this because it's easy. And the idea is to generate the first 10 Fibonacci numbers. So we create a vector to hold the results. We enter this loop, and each time we compute a Fibonacci number, we push it into the vector, and now return the vector. Easy. And how do you use it? For example, you can print it. You can, since vector as all the STL containers is a range, you can use it in the for range loop. And so you can iterate like this. X takes the value of all the Fibonacci numbers, and you can use print. I'm using this print. Print is also from C++23. It's like format, if you know this, if you know how format like. So it does formatting exactly that format, but prints directly to cout. Of course, there is a problem with this code because we have this comma here. But I like to keep the example simple. Actually, with ranges, the library from C++20 that introduced the ranges is going to use ranges a lot, and it is going to use ranges even more in C++23. So there actually is a nicer way to print this the sequence that uses println, just puts the range here, and the entire range will be formatted, included the square brackets. And here I use it println, so I also get a new line at the end. Okay, so let's see 2 more cases. Ranges are interesting, are a new thing that is good because allows to compose. Ranges can be composed with ranges algorithms, and we also have ranges view, which are facilities that take a range and produce another range. For example, suppose that I want to output not every Fibonacci number, but only the Fibonacci numbers that are even. Okay, that is easy. We just need to have, we just need to have a predicate that returns if a number is even. This is easy. And then we can use the filter views from the ranges library, the filter view, and compose with the pipe operator. And this, take this range and compose with this filter and creates a new range that only have the even elements of this one. So we print like this. Notice that filter is available right there in C++20, but be aware of this. You can't do this in C++20, unfortunately. There is a problem because this expression here creates a temporaries, and temporaries are destroyed before entering the loop in C++20. So don't try this in C++20, it's undefined behavior, but it is okay in C++23. because the rule for the destroying temporaries has been modified for the for-range loop especially. So this works in itCppCon23. Okay, let's see another example. I don't want all the even Fibonacci number. I just want all the Fibonacci number up to a certain value. For example, we could do the same thing as before. We can have this this predicate here. This predicate. This is, notice that this is a lambda that returns another lambda, so it's kind of a little more complicated than before. But anyway, it returns a predicate that checks if the given value is less than a specified maximum value. We could use filter as before, but we know that the Fibonacci number is strictly increasing. So as soon as one element of the sequence fails the predicate, we know that all the other ones will fail the predicate. So using filter would be a waste of time. So we can use a different ranges algorithm. We can use this. Take while. Take while takes the elements from a range up to a certain time, a certain place where the predicate stops being through. So this is, for example, we take all the first 10 Fibonacci number and take all of them while the predicate less than 20 is satisfied, and we have this nice sequence here. But here we are starting to see the limitation of this approach. What are the limitations? Suppose I have, I change the 20 here and put 100. If I put 100, then this sequence here stops before reaching 100. We saw in the previous slide that the 10th Fibonacci number is 55. There is another Fibonacci number before 100. It's 80 something. So we would be missing a value. On the other hand, so we if we want to have all the Fibonacci number up to 20, we need to have an estimation for this. And this is not good. The other thing is that even with these two numbers, we have computed all the Fibonacci numbers after the 13 just to discard them. So not only we have computed them, but we allocated memory for them, and so there is a waste of resources in this case. Not only that, allocating the vector and returning it like this always require to allocate the entire vector and compute all the elements, even if they are not needed. And there is one more subtle point, that we need to compute all the elements before the code that uses those elements can start processing them. The function computes all the Fibonacci number up to 55 and then gives them to the caller, and the caller starts processing them. Sometimes it would be nice to start consuming the elements while they are computed, not at the end of the computation. So do we have an alternative to the generation with the vector? Of course we have. We have this. This we can. I'm sure that many of you already seen this pattern before. This is for each-like. We changed the function from something that returns a value to a sort of algorithm that takes a callback. I Don't be fooled by the notation. This is a compact notation introduced in C++20. This is actually template because of this auto here. Invocable is a concept, it's not a type. So the type is STT invocable int auto. So this is a callback that is invoked here. So the code enters the loop, and when it starts here, calls back the caller code with the value that is being produced. What are the advantages of this? We don't need to allocate the vector. There's no vector here. And the caller is allowed to process the elements as soon as they are produced. Let's see how do we use this. This is the original version with the vector, and this changes a bit because now the loop is inside the algorithm and the body of the loop is inside the lambda. For example, you can use whatever callable you want, but with the lambda is easier. So the way to use this, this function changes a bit. It works exactly like this. Actually, this approach can be quite efficient. In fact, if you, for those, is anybody of you who is using the Unreal Engine? Because it was mentioned in the, no. In Unreal Engine, you will see a lot of functions like this. They also start with for each, whatever, for each, whatever. They're also like this. Okay. So this approach is actually more efficient, but it requires you to change the way you program. In particular, since there is no longer a range here to work with, you cannot use all the other things that we saw before. No way. You can't easily print with this approach as you do with the traditional approach. So do we have other alternatives? Of course we have. Second alternative, you can write your range. It's not hard. It's kind of boring because you need to provide a class, provide the iterator, put the state somewhere, implement the increment operator, increment the reference operator, implement the comparison between iterator and sentinel. Whew. You can do this. It's probably going to be the most performant way to achieve the goal, but the code will be very difficult to maintain and to read, especially if you have a computation that is more complicated than simply generate the Fibonacci numbers. So, okay, this is the most efficient way, but actually I wouldn't use it in production code unless profiling and performances, profiling has shown that performances are an issue. Okay, so we have a problem that has issues, two alternatives that solve some of the issues, but not all of them. What are the next alternative? Generator. This is how you would write the generator that does exactly the same thing that we saw before. You will see that is essentially the same as the other. It's essentially the same as the for each approach. There's no vector here. The invoke is being replaced by this co-yield. There is no invocable here, so there is no need to pass the callback. And the generator is put here, is the return type of the function. The presence of the co-yield here, the three co-keywords that start with co, triggers the coroutine machinery. So this is actually a coroutine. And I will not go into the details of coroutine syntax because it would take too long. But the presence of this triggers this new way of compiling this function. The generator contains a few rules to express to the compiler how this coroutine has to be interpreted, and so the magic happens. The idea is very similar to the one we saw before. So the value computed here is passed to the caller, and let's see how this happens. So generator is actually a range, so we can use it in the for range loop as we do with the vector. So this is correct. Let's expand a bit this for range loop. Okay, like this. So it's expanded like we did before. And then we can see how the flow execution is performed. So we start executing in this in the left part. So we reach the execution reaches this line, which calls Fibonacci 10. And this may be surprising if you're not familiar with coroutines, but this line here does not call this function here. It doesn't. It simply creates a coroutine context bound to this function and suspended. It is in suspended state. You can think about creating an object that has a handle to something that is stopped here. It's when we reach begin, instead suspend the execution of this function and then starts executing this function. It enters this function, the body of this function, initializes the variable, it enters the loop, and reaches the co-yield. Now, as soon as the value of b is computed and passed to the co-yield, this function is suspended again and returns like in that way. Hop. So, I'm sorry, I got back, but should we go forward? Okay. Now, this function is suspended here. Remember, we reached here, and then we resume this function that was suspended here and start executing like this. And we computed and returns a sentinel, which is not interesting here. Of course, iteration, the first time the iteration does not match the sentinel, then we enter here. The reference operation accesses B from that context. So this moves the value to the caller. Then we print the value, and then we increment the iterator. The increment of the iterator suspends again the caller and resume the generator from the suspension point, which executes this, computes the next Fibonacci numbers, and then loops, and then reach the yield again, and then go back to the caller, and so on. So the code goes back and forth from the caller to the coroutine when they reach the suspension point. So the suspension point here is the co-yield. The suspension point here is the increment of the iterator. It goes on like this until the generator stops. This test here ends because n go back to 0. The loop is broken. The function is finished. When the function is finished, the iterator is put into a state that matches the sentinel, and so the loop ends. So this is how generators work, and how coroutines, the interplay between the caller and the generator in presence of coroutine. How do you use it? You use it exactly the same as the vector example because it's a range with all. So you can do this, and you can do. You can compose with other ranges. You can, okay, of course, you can do this. And what about this example here? This is example here is a bit better because as soon as the generator computes the next element, which is 21, 21 is compared with this, and okay, it's no longer less than 20, so the loop, the iteration is abandoned, and you don't need to compute the other elements. So only the first one that is necessary because we have to compare it with the predicate, the first one is computed. All the other ones are not computed. But in what sense they are not computed? The caller is no longer calling the generator and is going to abandon the generator object returned from the calling Fibonacci 10 here. So the object is destroyed, and destroying the generator destroys the context of the generator. So in the right side of the previous slide, when we have the flow of execution, the code is not, the function is not completed. It's simply abandoned, and only the destructor of the local variables are called in that case. It's like if you put, where you have the co-yield, you get a goto to the end. Goto. I said the forbidden word. Okay. Remember that there was another issue here. What if we have this larger value here? Can we get, and we don't get all the Fibonacci number we wanted? Okay, that is easy. We can simply get rid of 10. We can write the generator like this, remove the maximum number, use an infinite loop, and expect the caller to abandon ourselves when he doesn't need more numbers. Of course, this code eventually overflows. Please, don't. Let's not get into that. So in this case, this is exactly like the same. We just need to change a bit here because in order to print only the first 10 Fibonacci number, we need to stop the iteration in some way, and the correct way is to use the take views from the ranges library. Take 10 takes the first 10 elements of the range. So this is the only difference with this new version of the Fibonacci generator. This one instead works in the same way. Okay. Everything's good? Okay, let's see a different way of using generators. We are no longer generating numbers, but suppose we need to provide in a sequence some data that is stored in a different data structure. Let's consider this data structure. I'm pretty sure everyone will recognize it. This is a classic binary tree, the node of a binary tree with the left branch, right branch, and some payload that I put in like this. And the problem here is to do, for example, a depth visit of this structure and print all the payloads of all the numbers. If anyone, I believe everyone, maybe as an exercise, has come to a solution like this. This is a classic visit approach, which resembles a lot the foreach-like approach we saw before. Let's check if the route is good. We visit the left branch and we return the payload, and then we visit the right branch. The payload is given to the callback, and when we visit the left and right branch, we just pass a copy of the callback. This works. I believe it's in the classic recursive function that is in all textbooks. So how do we write this with a generator? There are two ways. One is a bit naive, that is this one. You just iterate on the left branch and iterate on the right branch, and then yield, in this case, yield whatever is in the left branch, the payload, and whatever is in the right branch. This actually works, but I would not recommend to do this because it's very inefficient. Okay, I just finished this slide. This is very inefficient because if you have a very deep structure, imagine a leaf has to yield to the parent, that has to yield to the parent, that has to yield to the parent, that has to yield to the root. And so there is this chain of yielding and resuming that is taking too much time. Fortunately, we have a better way to do this, and it's this. This little wrapper here yield elements of the visit of the left branch and the payload, and the elements of the right branch. This is quite, once you get accustomed to the co-yield syntax, it's quite easy to read. So I would say this code is pretty maintainable. This element of does the magic. Actually, it works with every range. It iterates into the range and yields all the elements of the range. But if it detects as its argument a generator, it exploits what is called symmetric transfer and allows the nested generator to yield directly to the caller without passing through the stages. So this is very interesting and allows to do this kind of things efficiently. Time is up, so just only a recap. A generator is something that produces a value, etc. Okay, this is not very interesting. Of course, there is something that I didn't tell you, and that is unfortunately very important. There is a little overhead. It's not free because we need to allocate the coroutine context each time you call the coroutine. It's at least it's a cost that is constant. It's not like the vector, the initial example with the vector that if you require 100 Fibonacci number, you need to allocate a vector of 100 elements. You just need to allocate this little object that has a couple of pointers plus the size of all the local variables, but you have it. So in some cases, it's a cost that you don't want to pay, but at least you get a lot in maintainability and usage and ease of use of your functions. Okay. Generators are input ranges. Okay, this is only technical stuff. Just the last thing, the generators I presented generators with one, the first template argument. Actually, it has 3, but the other 2 are only for advanced usage. The second one are used to tweak some interaction with ranges when the object plays the role of reference. If you have a range that returns a string view actually is a reference to another string. So you need to tweak it a bit. And then you can customize the allocation of the context of the coroutine context. If you want to put it in a specific use your allocator, you can do this. Okay, so these are the references. The paper that presented the facility. There is an addition to implement for. No, sorry. This is the extension for polymorphic allocators, and this is the reference implementation. The link is actually contained in this paper, but okay. So thanks a lot for attention. And I guess that we have the last coffee break. But if you have questions, I'll be around here.